Good morning, everyone. In the previous class, we discussed the basic concept of a control system. So we learned what control system is and what are the major elements of the control system. The main elements of the control systems are process, then measuring element, then controller, then final control element. So then we also discussed different types of a control system. Those are like feedback and feed forward. Feedback controller and feed forward control systems. So the main difference between these two systems, how the variables are measured. Okay. In feedback control system, we measure the controlled variable, which is usually the output. It is usually the output, right? Output variable. Then we compare this measured value with the desired set point value. And based on the difference, the system adjusts the process. So this is called feedback controller. In contrast, the feed forward control system, we do not measure the controlled variable. We do not measure this one. And the controller, so here what we measure? Here we measure the load variables. This is what we measured, which is usually the input disturbances. This is what input for this process, which is usually an input disturbances, and the controller take action before the disturbance affect the process. Okay, so in the simple term, what we can say, load variables are input variables, control variables are output variables. Remember, it's very important. Load variables are the input variables, controlled variables are output variables. Okay, this is very, very important. Then we also discuss what to discuss, positive and negative feedback. Positive and negative feedback. So what is meaning of negative feedback? What is meaning of positive feedback? In the negative feedback, the error is equal to TR minus TM. Okay, where TR is the set point, TM is the measured variable. So the objective of negative feedback control system is to minimize the error. To minimize the error, ideally make it equal to 0. This system is called stable system. Very, very important. This system is called stable system, and therefore it is commonly used in most industrial process. This is very, very important in industrial process. So in the positive feedback, when you come to the positive feedback, the error is calculated equal to TR plus TM. This is here we're getting TR plus TM. Instead of reducing error, the system is increasing error, causing the system to become unstable. Okay, because of this instability, positive feedback control systems are rarely used in process industries. Okay, therefore the most practical applications, we prefer negative feedback control system. That's what we discuss here in PDC. Most of the time, negative feedback control systems. Okay, now we can discuss about our example, what we last time discussed about CSTR temperature controller. So to understand the control system clearly, we consider example of CSTR. This is what we discussed, right, last class. So in this reactor, feed enters the flow rate of W and inlet temperature Ti. And the reactor produces an outlet temperature of T. What is the objective? Our objective is to control the reactor temperature at desired value. That's called our set point. This is your set point value. This should maintain T here. Okay. Now let's see working of a control system. So first we place a temperature measuring device, such as thermometer, inside the reactor. That's called measuring element. Okay. This measuring element measures the reactor temperature and send signals called TM. The signal goes to the controller. It's called control recorder, maybe controller. Okay, inside the controller, the measuring value TM is compared with the set point value TR. Okay, so then control calculates the error. That means E equal to TR minus TM. Depending on the magnitude of the error, the controller sends signal to the final control element. So depending on the magnitude of the error, the control sends signals to the final control element. Okay. So this is what final control element. The final control element adjusts the heat input to the reactor. So this depends on how the heating is supplied. If the heating is medium as steam, the final control element is a pneumatic control valve. Okay. Suppose if heating media is electricity, the final control element may be the variable transformer. Okay. So the final control element changes the heat supply Q to this reactor. If the temperature is higher than the set point, heat supply will be reduced. If the temperature lower than set point, the heat supply will increases. Okay. So this cycle continuously until the error becomes approximately zero. Meaning the reactor temperature reaches the desired set point. Okay. So this is what we discussed last class very clearly. Okay. Then one more important topic we discuss here, block diagram representation. Okay. So let's see. It's very important. So to represent the control system clearly, we use a block diagram. Okay. So this block diagram shows the interaction between different elements of a control system. So what are those? Primary is the process, then measuring element, then comparator, then controller, and then final control element. So let's discuss one by one. What exactly the process? Discuss one by one. What exactly the process? So a process CSTR. Okay. The output from the process is the temperature T. So this is what controlled variable. Remember always, this is what controlled variable. So next one is measuring element. So here the temperature is measured using a thermometer. Then the measuring element produces signal Tm. This represents the measuring temperature. Then the signal will go to the comparator. This is called a summing junction. Okay. So next we have comparator also called summing junction. This is very, very important. So the comparator compares with set point TR, measuring element TM. The output from the comparator is error signal. This is equal to TR minus TM. That's what we discussed. So then what is the step 4? Step 4 is the controller. So the error signal goes to the controller. The control processes the signal and it sends a control signal to the final control element. Okay. For example, if you use a proportional controller, the output signal is proportional to the error. Anyway, we discuss later those things, but still. Then what exactly is the final control element? So here it will adjust the heat supply Q. That's what final control element job. So this heat input directly affects the reactor temperature. So now closing the control loop. So the system continuously measure the temperature and adjust the heat supply until the desired temperature is maintained. Okay, this is what the block diagram of a control system. It's very, very important. Then also we discuss two types of control problems. One is regulatory control problems, other one is the servo type of control problem. So the regulatory control problem is the set point remains constant. Here the set point remains constant. So the system raised to reject the disturbances. Suppose if you take some examples, chemical reactor. If you take a chemical reactor, so the temperature must remain constant, right? So even the inlet temperature changes, the control system must adjust the heat supply to the maintain the same reactor temperature. That's what we discussed till now. This is called a regulatory problem. Most of the chemical process control systems fall into this category only. Then we have a servo problem. So here the set point change with the time. So it will change with the time. So the control system must track the changing the set point. So best examples for this one, missile tracking system, missile. This was discussed last class. Please go through my last class for more input. Missile tracking system, or maybe the robotic motion control, or maybe the I think position control systems. So for these cases, the objective is to follow a changing the set point accurately. Okay, this is what we discussed till last class. So now after understanding this block diagram, the next step is to derive a transfer function for each component. Transfer function for each component. Let's understand why we need to develop a transfer function for each component. Why we want to develop a transfer function for each component here. Okay, in the previous class, what we discussed about each diagram, right? Okay, so each physical component. So for each block represents a physical component of a control system. That's what we discuss. However, block diagram we draw is only for conceptual representation. Okay, to analyze the behavior of this control system, to analyze the behavior of this complete control system, mathematically we need mathematical model of each block. Mathematical model of each block. So this mathematical model is called the transfer function. So it's called transfer function. A transfer function, what will say, this is what describes the relation between input and output of the system in a Laplace domain. In Laplace domain. So for each block in the control system, we must determine the relation between its input signal and output signal. For example, if you take this process, the input, what is the input? The input may be heat input Q. This is what one heat input Q, and temperature is Ti. These two are inputs. And the output of the reactor is temperature T. This is the T. So inputs are Q and Ti, and outputs are T. So then we should develop a transfer function for this process. Then for the measuring element, the input here is, what is input for the measuring element? This is called process temperature. For the measuring element, sorry, this is the measuring element. So for the measuring element, the input is the process temperature T, and the output is the measuring signal Tm. So then we should develop a transfer function for this measuring element. Then for the controller, the input signal is error E, and then output is control signal. The output is a control signal E. So what is the output of the control signal? That what will go there. Then what is the final control element? The input control signal. The input is for this control signal, and the output is the manipulate variable, such as the heat input. So once we obtain the transfer function for each block diagram, then entire control system can be represented mathematically, which is what help us to analyze the what is importance, which is what help to analyze the dynamic behavior of the system. That's what we want. Then second point is study stability. Then what is third point? Predict the system response. Response very, very important. Predict the system response. Then we can design better controllers. When we have the transfer function, then we can design a better controllers. So therefore, the next step of our analysis is to derive the transfer function for all the components of a control system. So now we'll start with the process transfer function. So to derive this process transfer function, we begin writing a unsteady state energy balance of the reactor. Now let us start with first block in the control system, which is process. So in our example, the process is CSTR. CSTR heating system. So inside the reactor, a liquid is inside the reactor. The liquid is continuously flowing, and heat is applied to maintain the required temperature. So our objective is to find the transfer function of this process, which means we want to find the mathematical relationship between the inputs and output of this reactor. Okay, now let's see what are the inputs and output of the process. Okay, so in this system, the reactor receives two inputs. How many? Two inputs, right? So the first input is inlet temperature TA. Okay, then second input is heat supply to the reactor, that is Q. Okay, the output of the process is the reactor temperature T. So the process has input variables and output. What are the input variables are Ti and Q. These are the input variables. What are the output? Temperature T. Okay, now write the energy balance equation. For the process. So we start with the unsteady state energy balance. So the general form of energy balance is heat input minus heat output is equal to accumulation. So that means, what it simply means, the heat entering the system minus the heat leaving the system is equal to the rate of heat accumulation inside the reactor. Okay, so the heat enters the system in two ways, right? That's what we discussed. So first, heat is supplied external to the reactor. That's what we denote as a Q. This is one input. Okay, second, heat enters the incoming fluid stream. This is the second input stream. So the incoming fluid enters the temperature Ti, the flow rate is W, and the heat carried by the fluid depends on its heat capacity, right? That's C. So the heat entering the reactor due to the feed stream can be written as this, what here, the heat in plus this, completely heat in plus the two heat inputs, Q plus WC into Ti minus T0. So here T0 is the reference temperature. This is the reference temperature. So therefore the total heat entering system is this complete two terms, heat in, these two terms, Q plus WC into Ti minus T0. Then heat leaving the system. So what is heat leaving? The outlet stream leaves the reactor at temperature T, right? So the heat carried away by its outlet stream is WC into T minus T0. Okay, that's what heat out. Then we have heat accumulation. So now let us consider the heat accumulation in this reactor. So this accumulation term can be written as rho Cv into dt by dt. That means mass into capacity into rate of change of reactor, mass into capacity into rate of change of reactor. That means mass means rho into V. That's called density. Rho will be density. That's called kg per meter cube. V for volume, that's for meter cube. So this will cancel, this kg will be there. Okay. So here rho will be the density of the fluid. V is the reactor of volume. C is the heat capacity. So now we can write complete energy balance equation. Okay. So now Q plus WC into Ta minus T0 minus WC into T minus T0 is equal to rho Cv into dt by dt. So this is the equation. So this is the equation. So this is the equation represents the dynamic behavior. Dynamic behavior of a reactor temperature. It's very, very important. This is the equation tells the dynamic behavior of the reactor temperature. Okay. So now we know what are the terms are here, each and every term. That's what we discuss. Now what we need to do, the next job is to introduce a deviation variables. Okay. At steady state, we know very well, at steady state temperature does not change with the time. That means dt by dt equal to 0. So now write the steady state equations. So from the equation 1, we can write QC plus WC into TIS, this is very important, at steady state minus T0 minus WC. This is the same thing here we are writing. So at steady state TS minus T0 equal to 0 because there is no change with the time. But for our convenience purpose, make it to dTs, rho into C into V dTs by dt. Okay. Now subtracting from 1 minus 2. That's what we're doing, right? 1 minus 2 at steady state we want. So now subtracting steady state equation. That means this Q minus this QS plus WC into TA minus TIS minus, because WC become a common, so that's what we are substituting here. T minus TS equal to rho CV into D common, that means T minus this TS by dt. Okay. Now these are the terms, remember, we define this deviation variables as the difference between actual value and the steady state value. That's the terms of T, Q, T dash. Okay. So substituting these deviation variable into the energy balance equation. That's what we're getting the final transfer function. Okay. Now see. Now applying the Laplace transform. Now apply the Laplace transform. So please remember what we done those steps to define a transfer function in the previous class lectures. Okay. Now let's see, apply the Laplace transform to convert the equation into S domain. That's what we'll do, right? Okay. Now let's see. First make it simple. So that's Q minus Q become a Q. This is what we discussed. It's WC into this TA dash minus T dash into rho C into dt dash by dt. Now apply the Laplace transform. Then we can get Q minus Q will be capital QS. Okay. Then WC into TI dash S minus T dash equal to rho CV into what is that? dt by dt. What is the dt dash by dt? We know very well S into T dash of S minus T dash of 0. This is a dy by dt formula for the Laplace domain. Okay, we know T dash of 0 will be 0. There is no change with the time. Thus become a 0. So now we got the final equations. This is the final equations. Now it's not the final equation. Now still we need to do some rearrangements. That means, so we should rearrange the equation to express the outlet temperature T of S. That means T dash of S in terms of the inputs. For the purpose, what we need to do, we need to divide the divided by WC, because there is a constant term you should use. So that means QS by WC plus TA dash minus T dash FS, and this WWC will cancel here. Here also WC will be there by WC. So these two terms are cancelled. Equal to rho into V by W, because the CC will cancel, S into T dash FS. Now rearrange this equation. Make it common of T dash of S. That means rho V by W into S plus 1 equal to QC by WC plus TA dash of S. Okay. Here we should think about what is rho V by W. This is what we define time constant of the process. That means tau equal to rho V by W, time constant of the process. So this parameter represent how quickly the reactor responds to change in the input. Okay, this is importance of this parameter. So now let's write the final equation. What is the final equation now? T dash of S is equal to 1 by WC into Q of S plus T dash of S into 1 by tau S plus 1. So this is the final equations. Otherwise, if you want to make it more easily, we are substituting as a tau. Maybe you can write two ways, either this way or this way. Okay, for the more clarity, just if you want to make it common of 1 by tau S plus, this will become. Otherwise, you can just simply write Q of S into the first term, T dash of S into second term. Okay, so this is your final transfer function. So this is the equation represent the process transfer function of a CSTR heating system. So it shows how the reactor temperature responds to change in the heat input and inlet temperature. Okay, this is very, very important. It's very, very important. The importance of the final diagram. Remember, this is the importance of final diagram. It shows the reactor temperature responds to change in the heat input and inlet temperature T. Okay. Now we'll see that with respect to block diagram, how this one. Now let us see the block diagram A. So here I will explain one of the important concept with respect to block diagram. There are two block diagrams I just shown here. Now let's go by one block diagram. So from the transfer function, we derived earlier, right? What is the T of S? T of S is equal to 1 by WC into 1 by tau S plus 1 into Q of S plus 1 by tau S plus 1 Ti of S, right? So from the equation, what we can clearly see that two inputs affect the output temperature. So what are the two inputs, sir? That is, this one is the Q of S, other one is the temperature T of S. So both these inputs influence the output temperature T of S, T dash of S, or maybe T of S. Okay. Okay. Now let's discuss about the first path. So the first block represents the effect of the inlet temperature, and then the transfer function between the inlet temperature and the reactor temperature is 1 by tau S plus 1. So this is what our inlet temperature, this is our 1 by tau S plus 1. The transfer between the inlet temperature and reactor temperature. Okay. Thus what is the second path here? The second block represents the effect of heat supply Q of S. So from the transfer function, the relation is 1 by WC by tau S plus 1. So we draw another block here. That's Q of S is equal to 1 by WC into 1 by tau S plus 1. So then we have a summing junction. So now both effects combine together. therefore using the summing junction. So the output of two blocks are added and produce the our final output. That's called our T dash of S or maybe T of S. So the diagram A clearly shows that two inputs independently influence the reactor temperature. Okay, this is what you should remember from this figure A. Now let's discuss about the diagram B. So this is a simplify another way of representing the same equation. So from the equation we can also write how we can write this equation. T of S equal to 1 by tau S plus 1 into TIS plus Q of S by WC. That's what even I showed you there. Okay, here we first had the two inputs and then pass them through a process block. So what is step 1 here? First heat input is Q of S. Pass through the block, that is called 1 by WC. This is the input Q. So this converts the heat input into an equivalent temperature effect. Then what is the another? Add the two inputs. So now the modified heat signal into the inner temperature signal added summing this junction. That's called this plus this one. Now this combined then passes through the process dynamics, that's called 1 by tau S plus 1. So finally we obtain the output of T of S. So what we can understand from these A and B is the both diagram A and diagram B represent the same mathematical model. So diagram A shows two parallel paths. Okay, diagram B shows summation of first and then process block. So both are mathematically equivalent. So that means what I can say, whenever a system has multiple inputs, affecting the same output, we can represent it using the parallel blocks or combining the inputs before the process block. Okay. So now let's see the block diagram. So till now we finish the process transfer function. We define the process transfer function because based on the input and output only we can identify the what is the transfer function. So now we need to derive the transfer function of measuring element. Okay, in any control system, after the process produce an output, we need to measure that output. So in our example, the control variable is the temperature, right? This is what our control variable. That's called temperature. So we use a thermometer. We use here thermometer. We use a thermometer to measure the reactor temperature. So this is what you do. This is measuring element here is the thermometer to identify the how much temperature inside the tank. Therefore, what we can say, therefore process output is T, measure value Tm. Okay. So now what is the purpose of measuring element? So the purpose of measuring element is to sense the actual process variables and send the information into the controller. So the measuring element converts the actual temperature T into measuring signal Tm. So now we need to identify the transfer function. So how to define a transfer function? So the transfer function for the measuring element is Tm by or maybe Tm dash by Tm of S by T of S. So this is represent the relationship between measuring element Tm and actual process temperature T dash of S. Okay. What is the dynamic behavior? How to find this one? So to find this one, we need to identify what is the dynamic behavior of the thermometer, because here we are using the thermometer, right? So how to find? So in most practical situations, the measuring element does not respond instantly. That's what you can see in the lab also. Okay, for example, suppose if thermometer takes some time to respond, the temperature changes because it won't give instantly, right? Because of this delay, the measuring element behave like a first order system. So we assume that thermometer follows a first order dynamics. So what is transfer function first order system? For first order system, the transfer function is 1 by tau s plus 1. You know very well. So we now come to this here point. That means here Tm by T of s, that is equal to 1 by tau ms, measuring rate tau ms plus 1. Okay, 1 by tau ms plus 1, where tau m is time constant of a measuring element. So here the time constant represents the response speed of thermometer. Response speed of thermometer. Now let's see the block diagram representation. Measuring element will be the, see, this is what your input. Okay, that's called 1 by tau m plus 1. This is what your output is called Tm dash Fs. So here input is actual temperature T of S, output is the measuring temperature Tm of S. So this measuring element does not measure instantaneously. So it introduces a small dynamic delay, which is represent a first order transfer function. Okay. So now what we obtained? So till now we have obtained the transfer function for what are things we obtained? Transfer function for the process and measuring element. Next, we will derive a transfer function for controller and final control element. Thank you.